Hello everyone, my name is Himal Sharma and I'll be presenting our paper titled Numerical Investigation of ZrN-ITO coded photonic crystal fiber based plasmonic refractive index sensor. So this is the outline of our presentation. Moving forward, I would like to give a brief background of our research. So it's particularly based on sensors. So we are quite well aware that there are many different types of sensors. For example, piezoelectric to electrochemical. But in our study, we have particularly focused on fiber optic sensors, which are an emerging technology of sensors, which has a very high sensitivity. They respond fast, and they have a wide range of refractive index detection. Now, these fiber optical sensors have many different applications, which ranges from medical diagnostics to environmental monitoring to biosensing. Now, to further emphasize on fiber optical sensors, here's a projected market capitalization of fiber optic sensors, which shows that within 2034, it has been expected that the market is to reach around US dollars of $7.7 billion at an annual growth of 9.78%. So that's huge. Now, speaking of optical sensing techniques, it can be further categorized into fiber Bragg greetings, microring resonators, and surface plasmon resonance based sensors. So in our study, we have particularly talked about surface plasmon resonance based optical sensors, since these are much more superior. Now, surface plasmon resonance is actually an optical phenomenon where we have these plasmonic materials, for example, gold, silver, aluminium, titanium. Now, these plasmonic materials has their own natural frequency of oscillation. Now, when incoming light photons hit these plasmonic materials, they actually create a um, electron cloud or surface plasmon near the metal dielectric interface. So we are actually going to use that optical phenomenon to apply in our sensing techniques. So here's a picture of a prism-based plasmonic sensor in figure 3, which shows that when the incoming light photons hit the prism, uh, at certain frequency, there's actually a surface plasmon resonance occurring, which creates an evanescent field, or it excites the electron cloud near the metal surface. Now, this further causes the particular analyte to bind with the ligand, which causes a change in the refractive index of the medium. So that change in refractive index can actually shift the resonance peak or the intensity and the SPR angle through which we can detect our particular analyte. Now the problem with these prism-based plasmonic sensors are that they are quite bulky and they're quite complex. So here in our study we have focused on photonic crystal fiber-based surface plasmon resonance sensors, since these photonic crystal fibers they are going to provide they're going to provide strong light confinement, and they're much flexible and durable. So these are fiber optics optical fibers which has these periodic air holes, and through which you can actually guide the light as you want. So it provides better sensitivity, and uh, also there's more enhanced light matter interaction in this fiber optic sensor based on photonic crystal fiber. Moving forward, so what we have seen is through literature review is that these conventional SPR sensors, they are typically based on gold and silver. Now we are quite well aware that gold is very expensive, and it also actually causes a high optical damping, and it broadens the resonance peak. And for silver, it is actually chemically unstable and it's much more prone to oxidation. And the photonic crystal fiber based sensors, uh, if we use internal sensing designs, we have to fill in the air holes with the analyte, which is much more complex and slow. So to address these limitations of the conventional SPR sensors, our proposed solution is that we are going to use an alternative plasmonic material called zirconium nitride. So this plasmonic material is much more cost effective. They offer precise light control and also improve sensitivity. And further, this material has actually it's very stable with a high melting point above 2000 degrees Celsius. And to improve our addition with the zirconium nitride and also enhance the plasmonic excitation, we have used a conductive layer called indium tin oxide. So this is the structure of our sensor based on photonic crystal fiber. As you can see, there are hexagonal pattern of air holes, and there are two open ring D-shaped analyte chambers, so that the light could be guided to the analyte much more precisely, so that there's an improved sensitivity. Now all of this design has been actually modeled using the finite element method in COMSOL multiphysics. Uh, and moving forward, we have actually modeled the material, the refractive index of silica and the dielectric functions of ZrN and ITO using the Selmayer's equation and the Drude-Lorentz model respectively. So to further explain the operating principle of these photonic crystal fiber based plasmonic surface plasmon resonance sensors, what happens is basically there's this core guided mode and there's the SPP mode. So when this core guided mode and the SPP mode they actually couples, or the frequency matches, there is actually going to be a sharp uh, loss in the there's going to be a sharp loss in the resonance peak here, as you can see, during the phase matching condition. So that phase matching condition causes maximum energy to transfer from the core guided mode to the SPP mode, and which due to the change in the refractive index, this resonance peak actually shifts, and that's how we actually detect the analytes. And for our study, we have focused on Y polarized mode, since it provides stronger plasmonic excitation compared to the X polarized mode. So this is the proposed experimental setup of our photonic crystal fiber, where we can see that there's this OTS, or optical tunable source, which guides the light into the photonic crystal fiber. And due to the change in the refractive index of the analyte, we can see that there's a shift in the resonance peak through which we can actually detect the particular analyte using the optical spectrum analysis by comparing with the reference signals. So this is our key findings. As you can see, that figure 8 shows the loss spectra of the proposed PCF SPR sensor, where we have worked on a wide range of refractive index ranging from 1.28 to 1.42, and our study has shown that the maximum wavelength sensitivity is around 5000 nanometer per refractive index unit, and for amplitude sensitivity it's 150. So we have further optimized our optical sensor. We have actually uh, optimized the layer thickness of the zirconium nitride as well as the ITO from 20 to 50, as you can see. And based on this optimization of the layers as well as the air hole diameters and the pitch, or the inter air hole distances of the photonic crystal fiber, our results show that that compared to the prior studies, our photon crystal fiber based on the zirconium nitride and ITO actually performs quite well, as you can see, compared with zirconium nitride based V-shaped sensor, which has around 3800, and furthermore with other plasmonic materials, for example graphene, azo, it shows that it has much more better wavelength sensitivity and could perform quite well in the range of 1.28 to 1.42. So to conclude our study, as you can see that we have investigated the potential use of zirconium nitride as well as an ITO layer to enhance the refractive index sensing of the photonic crystal fiber. And we have used dual side polished D-shaped analyte chambers, and that shows maximum wavelength sensitivity of 5000 and amplitude sensitivity of 115 across a wide refractive range of 1.28 to 1.42. So this actually yielded excellent plasmonic resonance properties with the traditional materials like gold and silver, and they could be actually potential alternative to achieving a high durability and broad range detection as an alternative plasmonic material as well. So our limitation of our study is we couldn't validate our results experimentally, but this could be done using the fabrication technique of stack and draw method, through which we can use the external microfluidic channels and see how it performs. So our future work, we would like to investigate how these sensing capabilities happens or occurs for different biomedical applications that could be blood glucose monitoring or even cancer cell detection across a specific refractive index range. And we'd also like to optimize the sensor length and to see how it balances the trade-off between the sensitivity and the attenuation of the signal as well. Furthermore, we'd like to optimize the airhole geometries, lattice pitch, as well as see other hybrid plasmonic materials or hybrid coatings, so that we could explore more materials compared to the traditional materials based on gold and other silver, for example. So these are the references of our slide. That is, thank you. Thank you for your time.